explain what is RWLock. In my previous video, we have seen what is mutex, how to acquire a lock, how to read the value, and also how to update the value. In this video, we are going to see how to do the same in RWLock, but with a different use case and also some small changes in the syntax. So RWLock is similar to the mutex lock, but the use case is different. Let's say we will use the mutex when we have very large number of write operations and also very minimal of read operations, or based on the real world traffic, this kind of read or write operation is unpredictable. In those scenarios, we will go with mutex. But the RWLock, we will go with RWLock when we have so many number of read operations and also very minimal write operations. Okay, so actually based on this use case, we will go with mutex or RWLock. Okay, and so coming to the characteristics of the RWLock allows multiple readers at the same time. Let's say we have 1,000 readers. 1,000 readers can access the same data at the same time, and that's not the case with mutex. Okay, in mutex, each reader or writer has to wait before the previous operation completes, and that's not the case with RWLock. Here, the RWLock allows multiple readers at the same time. Okay, and also when you want to update the value, when you want to write the value, this allows only one writer at a time, and while doing the write operation, any readers are not allowed. Okay, we have let's say 1,000 readers and only one writer, and 1,000 readers can read the data, but when the writer comes in, the readers has to wait before the writer completes its operation. Once the writer done with the update, then again it allows multiple readers to access the data. That's the basic explanation of RWLock. Okay, let's dive into code example. So what we are going to do is, first we are going to create multiple readers scenario where we will have R1, R2, and R3 simultaneously reading the count data. So first I am going to create the count and log it in using RWLock, and the initial value will be 0, or we can put let's say 100 and 100. Okay, I'm going to create 3 readers, R1 count.read 100. Okay, now we have 3 readers simultaneously reading the count data. Let's see what these 3 readers have got the data as, or 1 or 2 1. Let's run this program and see the output. Here we got the output as 100 for R1, 102, sorry, R1 100 for R1, 100 for R2, 100 for R3. Okay, so now these 3 readers can read the data simultaneously. There's no problem in that. Okay, we can scale this up to even 1,000 readers, 10,000 readers, and it can go on, no problem at all. But the problem is when the writer comes in. When the writer comes in while the readers are still holding the read lock, then it will be problematic. Why? I will explain. I will explain by running the program again. Okay. First, we will create a writer using the write lock. Okay, and we will update the value. To update the value, we will use mutex w1, and let's increase the value by 400. Now we will have the updated value of 500. Okay, okay, let's run this program, but it won't run, but I will run it. Just a second, sorry. Let's run this. Here we got the output from line 17, but not from line 20. Why? Because the readers are still holding the lock, the read lock, but when the writer comes in, it tries to acquire the write lock. Because of the readers still holding the lock, the writer couldn't acquire the lock, and it leads to deadlock because the readers are also holding the lock for it, and the writer is also trying to acquire the lock. And here the deadlock happens. Okay, so to avoid these scenarios, what we can do is we can do it in two ways. We can use the scope based unlock, or we can use the drop function to release the lock for leaders. Okay, first I will show an example using the temporary scope based unlock. Here I have put these leaders in a separate new temporary local scope, and when this local scope ends, it will releases all the locks acquired by these readers. Okay, once the lock has been released, then the writer can access the writer can get the write lock and can do its operation. Okay, let's run this. Here we can see the value has been successfully read, and also we can successfully update the value. Why? Because the reader's lock has been released. So we can use the scope based unlock, plus we can use the standard drop function. To do it, we can use the drop function from standard mem drop r1, r2 and r3. Let's run this again. Now we have the same output. That's good. Okay, let's move to the next part. Okay, now let's say a new reader comes in, r4 comes in. Okay, let r4 equal to count dot read and unwrap. Again, it will not work. I will explain. Print let's put okay, again it won't run. It won't run. I will explain. Okay, let's run this again. Now we have the output from line 25 but not from line 28 because the writer here still holds the lock. Okay, again we have to do the same thing. We can use the scope based unlock, or we can go with standard drop function. Now we will get the output from line 29. Here we can see. Okay, so the overall logic is so many readers can read the data at the same time, though the previously the lock acquired by reader still hasn't unlocked, because multiple readers can read the same. Multiple readers can read the same data at the same time, but that's not the case with writer. Same for when one writer writing the data and still not released the log, when new reader comes in, cannot do the read operation because the writer is still doing the write operation. So that's the overall logic. Okay. Sometimes when you are not sure whether you will get the log or not, what you can do is, let's go back to the writer scenario, and we will comment this drop function, which will lead to r1, r2 and r3 still holding the read log. Okay, instead of waiting for the lock indefinitely, what we can do is we can use the try write method. Node w1 count dot try write. Okay, now when we have successfully acquired the lock, we can update the data. If not, value, if not, okay, now let's run it again. Sorry. Here we are updating the value, so we have to place mute, and we can remove it from here, I think, if I'm not wrong. Yes, it's good. Lock couldn't be okay because these three readers are still holding the lock. Okay, even if one reader still holding the lock, we will get the same message. So we will release the logs and run the program again. Now we have successfully updated the value. Let's run it again. Yes, now we have successfully increased the value by 1. That's good. Same thing you can do for read also. When let's say when w1 count dot write back, and w1, let's say we will increase again by 100, 100, and print the value. Here the writer lock hasn't released yet, so again we will use the try read method. Count dot try read R4, we will name R4, name it as R4, match R4. If it's okay, then value let's run it. Here we got the message of couldn't acquire the lock because of the writer still holding the lock. Okay, so we can release the lock using drop function or scope based on lock. Once we have released the drop once we have released the lock for w1, then we can read the value, and it can go and it can go on continuously. Okay, I think that's it. So here you can get two types of error messages, I think. One is try lock error would block, okay, and another is try lock poisoned. Here poison error. Let's print the lock. I think we will not go into the details of poison. I will just explain the would block. Okay. Okay. So here we are getting two possible errors. One is poisoned and another one is would block. Would block is similar to the same logic that we couldn't acquire the lock due to the issue that is the lock is already held by some other reader or some other writer. Okay, and poison means when other writer, okay, I think it's only for writer in this case, not for reader. When other writer trying to write the data and something went wrong, the panic occurred, then it will poison the RWLock, and that will lead to the poisoned error message. Okay, I think that's it. Okay, thank you guys. I will see you in the next videos. Bye bye.